contact form redirects here. For a web email form, see form _ form to email scripts. In mathematics, contact geometry is the study of a geometric structure on smooth manifolds given by a hyperplane distribution in the tangent bundle and specified by a one-form, both of which satisfy maximum non-degeneracy condition called complete non-integrability. From the Frobenius theorem, one recognizes the condition as the opposite of the condition that the distribution be determined by a codimension 1 foliation on the manifold. Contact geometry is in many ways an odd-dimensional counterpart of symplectic geometry, which belongs to the even-dimensional world. Both contact and symplectic geometry are motivated by the mathematical formalism of classical mechanics, where one can consider either the even-dimensional phased space of a mechanical system or the odd-dimensional extended phase space that includes the time variable. Applications. Contact geometry has, as does symplectic geometry, broad applications in physics, e.g., geometrical optics, classical mechanics, thermodynamics, geometric quantization, and applied mathematics such as control theory. Contact geometry also has applications to low-dimensional topology. For example, it has been used by Kronheimer and Mistoka to prove the property P-conjecture and by Iacovelli-Ashberg to derive a topological characterization of Stein manifolds. Contact forms and structures. Given an n-dimensional smooth manifold M, and a point Pm, a contact element of M with contact point P is a dimensional linear subspace of the tangent space to M at P. A contact element can be given by the zeros of a one-form on the tangent space to M at P. However, if a contact element is given by the zeros of a one-form omega, then it will also be given by the zeros of lambda omega where lambda 0. Thus, lambda omega, lambda 0 all give the same contact element. It follows that the space of all contact elements of M can be identified with a quotient of the cotangent bundle T*M, namely, a contact structure on an odd-dimensional manifold M, of dimension 2k plus 1, is a smooth distribution of contact elements, denoted by Xi, which is generic at each point. The genericity condition is that Xi is non-integrable. Assume that we have a smooth distribution of contact elements, Xi, given locally by a differential one-form alpha, i.e., a smooth section of the cotangent bundle. The non-integrability condition can be given explicitly as: notice that if Xi is given by the differential one-form alpha, then the same distribution is given locally by beta equals f alpha, where f is a non-zero smooth function. If Xi is co-orientable, then alpha is defined globally. Properties. It follows from the Frobenius theorem on integrability that the contact field Xi is completely non-integrable. This property of the contact field is roughly the opposite of being a field formed by the tangent planes to a family of non-overlapping hypersurfaces. In M, in particular, you cannot find a piece of a hypersurface tangent to Xi on an open set of M. More precisely, a maximally integrable subbundle has dimension n. Relation with symplectic structures. A consequence of the definition is that the restriction of the two-form omega equals d alpha to a hyperplane in Xi is a non-degenerate two-form. This construction provides any contact manifold M with a natural symplectic bundle of rank 1 smaller than the dimension of M. Note that a symplectic vector space is always even-dimensional, while contact manifolds need to be odd-dimensional. The cotangent bundle T*n of any n-dimensional manifold N is itself a manifold and supports naturally an exact symplectic structure omega equals d lambda. There are several ways to construct an associated contact manifold: one of dimension 2n-1, one of dimension 2n plus 1. Projectivization. Let M be the projectivization of the cotangent bundle of N. Thus M is fiber bundle over AM whose fiber at a point X is the space of lines in T*n, or, equivalently, the space of hyperplanes in Tn. The one form lambda does not descend to a genuine one form on M. However, it is homogeneous of degree 1, and so it defines a one form with values in the line bundle O, which is the dual of the fiber-wise tautological line bundle of M. The kernel of this one form defines a contact distribution. Energy surfaces. Suppose that H is a smooth function on T*n, that E is a regular value for H, so that the level set is a smooth submanifold of codimension 1. A vector field Y is called an Euler vector field if it is transverse to L and conformally symplectic, meaning that the Lie derivative of d lambda with respect to Y is a multiple of d lambda in a neighborhood of L. Then the restriction of to L is a contact form on L. This construction originates in Hamiltonian mechanics, where H is a Hamiltonian of the mechanical system with the configuration space n and the phase space T*n, and E is the value of the energy. The unit cotangent bundle. Choose a Riemannian metric on the manifold N and let H be the associated kinetic energy. Then the level set H equals 1/2 is the unit cotangent bundle of N, a smooth manifold of dimension 2n, one fibering over N with fibers being spheres. Then the Liouville form restricted to the unit cotangent bundle is a contact structure. This corresponds to a special case of the second construction, where the flow of the Euler vector field Y corresponds to linear scaling of momenta p's, leaving the q's fixed. The vector field R, defined by the equalities lambda equals 1 and d lambda equals 0 for all vector fields A, is called the REEB vector field, and it generates the geodesic flow of the Riemannian metric. More precisely, using the Riemannian metric, one can identify each point of the cotangent bundle of N with a point of the tangent bundle of N, and then the value of R at that point of the cotangent bundle is the corresponding vector parallel to N. First jet bundle. On the other hand, one can build a contact manifold M of dimension 2n plus 1 by considering the first jet bundle of the real valued functions on N. This bundle is isomorphic to T*n times R using the exterior derivative of a function. With coordinates, M has a contact structure alpha equals dt plus lambda. Conversely, given any contact manifold M, the product M times R has a natural structure of a symplectic manifold. If alpha is a contact form on M, then omega equals D is a symplectic form on M times R, where T denotes the variable in the R direction. This new manifold is called the symplectization of the contact manifold M. Examples. As a prime example, consider R3, endowed with coordinates and the one form dz minus y dx. The contact plane shear to point is spanned by the vectors x1 equals y and x2 equals x plus yz. By replacing the single variables x and y with the multivariables x1, xn, y1, yn, one can generalize this example to any R2n plus 1. An important class of contact manifolds is formed by Sasakian manifolds, Legendrian submanifolds and knots. The most interesting subspaces of a contact manifold are its Legendrian submanifolds. The non-integrability of the contact hyperplane field on a dimensional manifold means that number 2n dimensional submanifold has it as its tangent bundle, even locally. However, it is in general possible to find n-dimensional submanifolds whose tangent spaces lie inside the contact field. Legendrian submanifolds are analogous to Lagrangian submanifolds of symplectic manifolds. There is a precise relation. The lift of a Legendrian submanifold in S-symplectization of a contact manifold is a Lagrangian submanifold. The simplest example of Legendrian submanifolds are Legendrian knots inside a contact 3-manifold. Inequivalent Legendrian knots may be equivalent as smooth knots. Legendrian submanifolds are very rigid objects. Typically there are infinitely many Legendrian isotopy classes of embeddings which are all smoothly isotopic. Symplectic field theory provides invariants of Legendrian submanifolds called relative contact homology that can sometimes distinguish distinct legendary and submanifolds that are topologically identical. REB vector field. If alpha is a contact form for a given contact structure, the REB vector field R can be defined as the unique element of the kernel of D alpha such that alpha equals 1. Its dynamics can be used to study the structure of the contact manifold or even the underlying manifold using techniques of Floer homology such as symplectic fields theory and embedded contact homology. Some historical remarks. The roots of contact geometry appear in work of Christian Huygens, Isaac Barrow and Isaac Newton. The theory of contact transformations was developed by Sophus Lie, with the dual aims of studying differential equations and describing the change of space element, familiar from projective duality.